The binomial theorem is about an important shortcut that crops up more often than you would guess. It specifically refers to the situation where you have a binomial, two terms, like a plus b, something like this, raised to some kind of an exponent. Now, when the exponents are pretty small, like 0, 1, or 2, the answers are completely trivial, and you know what the answers are from basic algebra. Like anything to the 0 is 1. A plus b to the 1 is just a plus b. A plus b to the 2, well, that's a plus b times a plus b. You square it out, and you get a squared plus 2ab plus b squared. For a plus b to the third, now you're kind of pushing it a little bit, where you might think that perhaps you take the previous answer and you multiply by another a plus b, so you've got to distribute in the a and distribute in the b and collect like terms. But you can see this is going to become a really bad idea if your exponent keeps getting bigger. If you're trying to deal with something like a plus b to the 7th, do you really want to keep multiplying in a plus b's over and over and over again? That's going to be a lot of work. So the binomial theorem is meant to be a shortcut to help you work these things out for larger exponents where you don't want to do it directly, where you don't want to actually multiply everything out. And there are really going to be 3 different shortcuts that are going to work sort of all in conjunction with each other here. One of the shortcuts, one of the patterns that we're going to exploit here, is the pattern that you can see in the exponents on the a's and b's. So notice, like with a plus b to the 4th, if you put everything in some sort of organized order when you collect your like terms, you're going to start off with an a to the 4th, and then as you go through the terms, the exponent on a keeps getting smaller. 4, 3, 2, 1, and then it's gone. And in reverse, while the a's are disappearing, the b's are replacing them. So it's going to end with b to the 4th. So you've got a pretty predictable pattern. If I asked you to just work out the a and b exponents for a plus b to the 5th, you can probably guess what they're going to be. It's going to be an a to the 5th to start. Then there's going to be an a to the 4th b. And then there's going to be an a to the 3rd, b to the 2nd. And then you're going to have a to the 2nd, b to the 3rd, and so on. So the pattern for the exponents, that part's not challenging. If I were to skip ahead and say, let's work out a plus b to the 7th, you might feel intimidated about the coefficients, like the numbers that go in front of these terms. But the exponents themselves should not be too bad. So let me take a second to write down the exponents. And then we're going to talk about the part that's harder. The harder part here is the coefficients, clearly. I mean, you can see that those don't seem to follow as quite an easy of a pattern. There's something else going on there. So we're going to need some kind of shortcut for the coefficients, and that's really where the binomial theorem kicks in. The binomial theorem is really about the coefficients. All right. Now, for the coefficients, you have 2 different options. As long as your exponent is still kind of smallish, like 7 is not too bad, 8 or 9 is okay. As long as your exponent is still kind of smallish, then the coefficients can be created by a thing called Pascal's triangle. Pascal's triangle has been around for a really long time, and in fact Pascal did not invent it. The only reason we call it Pascal's triangle is because Pascal found out that you could use it for things like the binomial theorem and a lot of other stuff as well. So he's not the inventor, but he is the person that found a way to make it useful. So Pascal's triangle is not a complicated thing. If you just look at the coefficients from these first several rows, like take out the a's and the b's and the pluses and just look at the numbers, you'll see these numbers. And the pattern in these numbers is actually a pretty simple one. You add together pairs of numbers to get the next number down in between them. So like 1 and 3 makes 4, 3 and 3 makes 6, 1 and 3 makes 4. So if you were to continue this pattern further, you would have 1 and 4 makes 5, 4 and 6 makes 10, 6 and 4 makes 10, 4 and 1 makes 5, and so on. This is actually a really easy pattern to write out as long as the numbers aren't getting too big. They do eventually get pretty big. We're already into 2-digit numbers, and you can sort of see where this is headed. Pretty soon we're going to have 3-digit numbers, and by that point you're going to say, well, I'm not so sure I like this anymore. But at first, you end up getting workable numbers, numbers that don't really strain your brain. Those numbers will be the coefficients. So if you're doing the 7th power, like we are here, notice that this second number in Pascal's triangle is always the same as the exponent, so it becomes really easy to see which row you're trying to use. If the exponent's 7, you're going to use this row. And our coefficients are these ones. So 1, 7, 21, 35, 35, 21, 7, and 1. This part of the binomial theorem is relatively straightforward. The pattern for the exponents is easy. The pattern for the coefficients is a little harder, but not too bad. And it is a little tricky that you have two patterns going on at once that you're kind of dealing with independently. But the actual hard part about the binomial theorem is that usually the A and B aren't just A and B. Here, A is 3x, and B is negative 2y. So what that means is that all the work we just did in purple up at the top of the screen here, that's really sort of a formula. That's not the answer. That's just a formula we're going to use to create the answer. We're going to have a to the 7th. Okay, but it's not just a. That's going to be 3x to the 7th. So then you're going to have to work out what 3 to the 7th is. 3 to the 7th is 2187. So that first term ends up a lot more complicated than it appeared. The second term is 7a to the 6th b. Well, except it's not just a and b. A is 3x, b is negative 2y. So this term, you've got to work out 7 times 3 to the 6th times negative 2, and you get negative 10,206, x to the 6th y. So this is really the hard part about working with the binomial theorem. The formula that you create from the patterns, that's pretty straightforward. Plugging into that formula all these little fiddly numbers and working out all their little tiny exponents and multiplying all the results together. Like here we got to go 21 times 3 to the 5th times negative 2 squared. That gives you 20,412 x to the 5th y squared. This is the hard part about doing the binomial theorem. So just because you've got the a's and b's, I don't think you're even halfway done at that point. Getting the A and B pattern from Pascal's triangle and from the pattern for the exponents, that's a quarter of the work, maybe. You're going to spend way more time filling in all the little parts of the A's and B's and working out each individual term. You can also see that because of how much work there is in that second stage, this is a tough, time-consuming problem, even when the exponent is 7. If you go to an exponent of like 10 or 11 or 12 or something like that, you probably just throw down your pencil and give up. You're just like, you know what, this is going to take too long. This is not a good question. It would be, if I put a question like this on the test, that would be really unfair because it would take you like 45 minutes just to work this one problem. So there's a different version of the binomial theorem that specifically is used for larger exponents, up like 9 or 10 or 11, somewhere above that, where we don't ask you anymore to do the entire expansion, because that's just kind of a crazy amount of fiddly little work that doesn't really make sense. So the advanced version of the binomial theorem is about working out a single term in isolation all by itself. Now, how are we supposed to do this? Are we supposed to do Pascal's triangle? No. Doing all of Pascal's triangle just to get one individual number. And if you're talking about exponents like 10 or 11 or 12 or something like that, that's a lot of Pascal's triangle for one single number. The good news is there's a very, very simple formula for what this coefficient ought to be. It's not difficult at all. The overall exponent goes in the numerator with a factorial, and then these two individual coefficients, or individual exponents, they go in the denominator. And that's it. That's the coefficient. N factorial over R factorial Q factorial. And when you're working any individual problem, it should be pretty obvious what n is, because that'll be part of the question. They'll say blah, blah, blah to the 10th or something. And then the R and the Q are whatever term you're looking at. In the textbook, though, and I've seen this in every textbook ever, they do something where they think they're helping you out. They think they're simplifying the problem for you. But they're actually making this formula trickier. What they notice is, in the pattern we were just working on the previous page, notice how anywhere you are for any individual term, the two exponents always add up to the total exponent. So when you're doing a plus b to the 7th, each term, the two exponents add up to 7. When we were doing a plus b to the 5, the two exponents always added up to 5, and so on. So here's what they do. They say, hey, guess what, folks? R plus Q always adds up to n, so we don't actually need to use the letter Q. We only need to use 2 letters of the alphabet instead of 3 letters of the alphabet. Now, that sounds useful. That sounds like a good idea, but take a look at what that does to the formula. It takes this coefficient here, and it turns it into a messier formula that is less connected to the pieces that you are working with. When it's just n, r, and q, it's really obvious which piece goes where. But here you've got this n minus r piece that kind of throws you off. The other thing that's really kind of interesting about this is, look at this formula. Haven't we seen this formula before? That's right, this is the combinations formula. The formula for figuring out if you choose from a set of n thing and you're picking r of them. This is the combinations formula. This is an example of something that we see quite a bit in advanced mathematics, where formulas and ideas that are appearing in totally unrelated areas, like binomial theorem versus permutations and combinations. Totally different areas of mathematics, yet there's these weird links that don't seem like you would guess that they would be there. So this is one of the first good examples of a really weird link in math. Binomial theorem is somehow linked to combinations. So let's do a quick example of how this formula would apply if you were doing a plus b to the 13th, and let's say we were working out a term that had a to the 5th, b to the 8th. Notice 5 plus 8 adds up to 13. Then the way you would work out the coefficient is you would have 13 factorial in the numerator, and you would have 5 factorial, 8 factorial in the denominator. And of course, just like when we were working with permutations and combinations, if you write out those factorials, there will be loads of cancellation, just scads of cancellation. It'll simplify far more than you would normally expect. Just like in the other circumstance, this here is not usually the final answer, because most of the time you've got an a and a b that are not just a and b. Like here, a is x and b is square root of 2. So the way you would work a problem like this is, first of all, figure out what your exponents need to be, and if you want to get x to the 5th, and you're going to be plugging in x for a, then you're going to have a to the fifth. In other words, the coefficient and term that I just worked a moment ago. So, if you do all that factorial stuff, you get 1287. Then you have to plug in for the a part, and you have to plug in for the b part. And just like in the previous problem, this part is probably more work than the part that got us here, that got us the coefficient and the exponents. The square root of 2 to the 8th, that part, that's the same as 2 to the 4th, so that's 16 in other words. And 16 times 1287, you get 2592. One last little tricky part in this problem. It's not a massive challenge, but it's something you need to be thinking about. The question asks you for what is the coefficient. So this is kind of a vocabulary question. When you look at a result like what we have at the end of this, and you're thinking about the word coefficient, realize that the coefficient is just this part. X to the fifth is not part of the coefficient. 20,592 is the coefficient of x to the fifth. So x to the fifth is not part of the answer. It's a little fiddly detail, but that's the sort of thing that makes the difference between a student that gets a B and a student that gets an A. Pay attention to vocabulary. And this is the type of binomial theorem you'll use with larger exponents. The Pascal's triangle version is what you'll use with relatively smaller exponents. And there's no hard rule about where the cutoff is. It's definitely somewhere between 7 and 13. So sometimes 9 or 10 is too big, sometimes it isn't. You just have to deal with which problem. A good giveaway would be, if the exponent is small enough, I won't ask you for an individual term. For smaller exponents, I'll ask you to do the full expansion, like we started here in this example. But just out of practical considerations, I can't use an exponent that's too big for something like that, because I need the problem to take less than 45 minutes, of course.